Welcome. In this general chemistry tutorial, we'll look at calculating the pH of a weak acid solution using the acid ionization constant Ka. So we want to determine the pH, percent ionization, and equilibrium concentrations of a 0.050 molar HF solution. And we're given the Ka of HF as 7.2 times 10 to the minus 4. We start with the ionization reaction. The acid HF reacts with water to produce fluoride ions as well as hydronium ions. We begin with an ice table. We can plug in the initial concentrations. We have 0.050 molar HF and 0 concentration of our products. The change is how the concentration changes over time. So minus X for HF plus X for both of the products. So our equilibrium concentrations will be 0.050 minus X for HF and X for both F minus and H3O plus. Setting up our Ka expression. Like any equilibrium expression, it's the concentration of the products over the reactants. We do not include water because it's a liquid, it's our solvent. It does not get included in the Ka expression. In terms of X, Ka is equal to X squared over 0.050 minus X. In order to make the math a little bit simpler, we can make the assumption that X is going to be very small. We can do that when the acid concentration is high, when it's greater than 0.1 molar. Our problem doesn't meet that requirement. We can make the assumption when Ka is very small, when Ka is less than times 10 to the minus 4, we're right on the line with that. Or if the percent ionization is less than 5%. So let's go ahead and solve it as if X is very small. That means we'll set up our Ka expression equal to the 7.2 times 10 to the minus 4 and solve for X. We find that X is equal to 0.0060 molar. And if we go back to the ice table, X represents the hydronium concentration. So we can find the pH by taking the negative log. pH is equal to 2.22. Finding the equilibrium concentrations, we solved for X. So that would be the concentration of both fluoride and hydronium at equilibrium. To solve for the HF concentration at equilibrium, just take the initial 0.050 minus X. So we get an equilibrium concentration of 0.044 molar. The percent ionization takes the hydronium concentration at equilibrium and divide by the initial acid concentration and multiply by 100. That gives us a percent ionization of 11%. That's greater than 5%, so we don't meet the requirements of making the assumption that X is very small. So we need to solve this problem by using the quadratic equation. So we go back to our original ice table. We set Ka, the expression, equal to the Ka value But here we can't simplify the denominator. We're going to leave in that minus x. So we need to distribute, rearrange, and we end up with an expression that looks like this. X squared plus 7.2 times 10 to the minus 4x minus 3.6 times 10 to the minus 5 equals 0. To solve for x, the quadratic equation is listed at the right. So the coefficients in order are A, B, C. So A is 1, B is 7.2 times 10 to the minus 4, and C is the minus 3.6 times 10 to the minus 5. Plugging those values into the quadratic equation, we'll find that x will give either a positive or negative concentration. The one that gives a positive concentration uses the plus before the square root. So we find that x is equal to 0.0056 molar hydronium, which means our pH is 2.25. Now let's compare. When we used the assumption and simplified the math, we had an x equal to 0.0060 molar and a pH of 2.25. Without the assumption, x was 0.0056 and a pH of 2.25. That might not seem like a significant difference, but it is more accurate. It turns out that the HF concentration was still the same, 0.044 molar. And the percent ionization is, again, 11%.